Hi everybody. I wanted to make a couple of videos about polynomials and try to start tying everything together. So in this example we're going to do just that. So we have this polynomial function 2x cubed plus x squared minus x plus 3, and we're going to be thinking about this algebraically and trying to find its zeros, trying to factor it, and we're also going to be thinking about this function graphically. And all of these things are interrelated. It doesn't really matter where we start. There's some things that we need to have committed to memory, and there's reasons for all of it, but at the end of the day we'll commit it to memory. So over here where we're thinking about the graph, since that's a third degree polynomial, I know that it can have at most 2 turning points, so that tells me something about the graph. And then for the end behavior, we use the leading term test, so I just look at the first term, 2x cubed, and we'll say to ourselves, well, as x goes to infinity, what happens to the function values? So we're thinking about a big positive number for x, raise it to the third power, you're still positive, multiply by 2, you're still positive. So as x goes to infinity, the function values go to infinity. And then we do the same thing for our end behavior on the left. As x goes to negative infinity, what happens to the function value? And I mean, you might have memorized that, if it's an odd degree polynomial, then the end behavior is different, so this is going to be negative infinity. Or you just think through the leading term test again. We have a big negative number, then you raise it to the third power. That's a big negative number, multiplied by 2, that's still a big negative number. So there we go, that's the end behavior. So I know on this graph, eventually if I go far enough to the left, the graph's going to be way down there. And if I go far enough to the right, the graph will be pointing up. So I do know that much. Now, notice that tells you one thing automatically, or something else automatically. We're going to have to cross over the x-axis if we're going to obey the end behavior. So I know that this function has at least one real zero. So let's think, is there anything else that we know right off the bat? Sure. If you plug in x equals 0, the function value is 3, so you know the y-intercept of the graph is at 3. That tells you something at least. All right, so we already know a little bit about the graph without doing any work. So now let's start thinking about the algebra. We would like to find the x-intercepts, the zeros. The zeros will be x-intercepts if they're real numbers, not however if they're complex numbers. So we want to find the 3 zeros that this function has. Since it's third degree, we know there will be 3. So the rational zeros theorem is a really good place to start. It tells you the possible numbers that could be rational zeros of the function. So we know from the theorem that the possible rational zeros are the plus or minus p's over q's. Here we're at the little letter p and q. So we write the factors of 3 over the factors of 2, plus or minus of all of them. I'm kind of lazy, so I just want to write 1 plus or minus sign. So the factors of 3 are 1 and 3. The factors of 2 are 1 and 2. So there aren't all that many possibilities here. We have 1 over 1, 1 over 2, 3 over 1, and 3 over 2. So a plus or minus of all of those. So not too many possibilities. Now, Cauchy's bound is a theorem that I like because it takes no work. You do the whole thing in your head. It's sometimes not very useful. Let's see if it's useful in this case. So we want to find a bound that will contain all the real zeros, or an interval that contains all the real zeros. So what you do, ignore the leading term, and you look at the coefficients and the constant term, ignoring sign. Choose the largest one. That's 3. Then we divide by the leading coefficient. So we have 3 over 2. 3 over 2 is 1.5. So if you remember the theorem, that's in our book denoted capital M. So we have 1.5 as our capital M. We add 1 to that, so we have 2.5, and that gives us Cauchy's bound. So all of the real zeros have to live between negative 2.5 and positive 2.5. So in this case, unfortunately, Cauchy's bound wasn't very useful because the rational zeros theorem, the biggest number in that list was 3 over 2. Oh well, it was worth a try. Okay, now let's talk to our friend Descartes. He'll tell us how many positive real zeros or negative real zeros this polynomial might have. Now the positive side of Descartes is very simple. You just look at the function and you count the number of sign changes in the coefficient. So the +2 to +1, that's not a change. +1 to -1, okay, that's a change. So make a little mark, that's one sign change. And then -1 to +3, make 2 marks. That's 2 sign changes. So there could be 2 positive real zeros, but you have to count down by 2 until you either get to 0 or 1. So this function could have 2 positive real zeros, or it might not have any positive real zeros at all. Now, to find the possible number of negative real zeros, you have to do a little bit of work. You might be able to do this in your head. If not, what you have to do is find f of -x. So we're going to write the function down again and replace x with -x and see what happens with the exponents. So to the third power, that's going to be -2x cubed. The next term stays the same because negative raised to an even power, so it's still going to be positive. Then that term changes sign, and we have +3. So now we count the sign changes of f of -x. And as you can see, there's only one when I go from the leading coefficient, -2, to the next coefficient, which is positive. So Descartes' rule of signs was actually kind of useful here. I know that there's a negative real zero. So when we start doing synthetic division, which is the next step, I need to probably focus on the negative numbers. All right, so let's set up our synthetic division table. Here's a space for my divisor, and now my dividend is 2, 1, -1, 3. I like to block off the remainder. And now, unfortunately, you do have a little bit of trial and error here. Most people try to do a little bit of mental arithmetic, but at the end of the day, you have a list of numbers to choose from. You can try every single one of them if necessary. But like I said, I'd probably start with the negatives on this one. So, in the interest of time, you can try all of them. Eventually, you would try -1.5 or -3/2. So, the synthetic division algorithm, you bring down the first, the leading coefficient, then you multiply. -3/2 times 2 is -3, and then we add the 2 terms above the line. So -3 plus 1 is -2. -2 times -3/2 is +3. Now we add these 2 terms. 3 minus 1 is 2. 2 times -3/2 is -3, which gives us a remainder of 0. Now I knew that was going to happen. I kind of cheated and did it before. But like I said, worst case scenario, you just have a few options to try. Now, that means we have found a 0 of this polynomial. We know that -3/2 is a 0, but what we've also done is we've started to factor this polynomial. So I can start writing this in factored form if I need to. I'm going to write it just to sort of emphasize what we're doing here. If -3/2 is a 0, x minus -3/2, or x plus 3/2, that's a factor of my polynomial. And then the other factor is given in the bottom line of the synthetic division table. So this is the quotient when you're doing the division. So I'm going to reinterpret these numbers as a polynomial, and I know it's going to be a second degree polynomial. So I'm going to have 2x squared minus 2x plus 2. So we have this linear factor, first degree factor, corresponding to this 0. So now we have 2 more zeros to find, and they're going to come from this factor. Now, if you tried to simply factor this like you would in Algebra 1, you're not going to have any success. This is an irreducible quadratic. Now, if you notice that it has a common factor of 2, I guess you could go ahead and take that out if you wanted to, like so. We could take out that 2, makes our lives a little bit easier. And then that factor is just x squared minus x plus 1. Okay, so I need to find out what zeros come from this factor. So I'm going to run out of room here. I'm just going to go down here and we'll find the zeros that come from that. So we have x squared minus x. I'm going to go ahead and skip the first step. I want to set this equal to 0. I'm going to solve this equation by completing the square. It won't factor, so that wouldn't be a good idea. You could use the quadratic formula if you want, but as you guys know, I hate the quadratic formula. That's my own personal bias, though. I like to complete the square. So to complete the square, the coefficient in front of the linear term, this is -1. The negative doesn't matter. The number I put in this blank space, half of 1 is a half. A half squared is a fourth. So I add a fourth to both sides. Now I can factor the left-hand side. It's x minus 1/2 squared. On the right-hand side, I have 1 over 4 minus 4 over 4. That's -3 over 4. When I take the square root, I'm going to go ahead and do 2 steps in one. I'm going to take the square root, and I'm also going to add 1/2 to both sides just to save us a little bit of space. So I have 1/2 plus or minus, because I took a square root. The square root of -3 is I root 3, and the square root of 4 is 2. So if you want to make this look a little bit prettier, since we already have a common denominator, the 2 other zeros, these are complex zeros, are 1 plus or minus I square root 3 over 2. So now we have all of the zeros of this polynomial. We found -3/2 by doing synthetic division, and then just using some algebra, we found the other 2 complex zeros. So I could, if I wanted, go back and write this polynomial in completely factored form. I have x plus 3/2 as a factor, and now I have 2 more factors that come from these 2 zeros. Now, unfortunately, writing these factors is not a large amount of fun, especially with a little tablet pen, so I'll do my best here. But if these are zeros, x minus those zeros will be a factor. All right, so that's the polynomial written as a product of linear factors. And always make sure to check that your leading coefficient matches. If you spend a lot of time thinking about zeros, sometimes you'll forget what the leading coefficient needs to be. So back to the original polynomial, I know the leading coefficient is 2, so we didn't lose it. We do have this leading coefficient of 2 here, and that all makes sense. If you want to go back to your graph now, we did find a real zero, and a real zero is going to correspond to an x-intercept, so we have an x-intercept right here at -3 over 2. So we could sketch a quick graph of the polynomial if we wanted to. I'm not, because we're not going to have all of the details in it. We don't know. Now we know it has at most 2 turning points, but I don't know exactly where those are. There are methods in calculus for finding those, but that's for calculus, not for us. So if you want to see what the graph looks like, I would just graph it in your calculator. That's fine. So we'd have to, we know the graph's going to be down here. We know the graph is going to cross over at this x-intercept because it's multiplicity 1. We know we're going to have to cross at this y-intercept, and we might have a couple of turning points at some place, and then the graph is going to go up. So anyway, this covers most of what we need to know about polynomials, but by far, or not nearly everything. But this is one complete example, and I'm going to make 1 or 2 more videos that have some things that don't show up in this particular example. So anyway, hope this helped. See you later.